Hi guys, welcome back to my channel. Today we're going to be looking at forces that depend on velocity. So previously we've looked at forces that depend on time, and we knew that when we were looking at these forces that acceleration was not constant. So we've got a similar concept here, but instead of force being a function of time, we're actually going to have force as a function of velocity. So when we do this, rather than writing our function ft is equal to mx, then we're going to write fv is equal to mx. So when we're looking at my x value there, so that's the second derivative of x, I should say, and that is the second derivative of displacement or acceleration, that's still going to be equal to the change in velocity over the change in time. But we're no longer integrating with respect to time. We're going to want to integrate with respect to velocity. So we're going to have to rearrange before we integrate. So here's an example. A body of mass 2 kilograms moving in a straight line is opposed by a force of V minus 8 newtons, where V is the velocity in meters per second. Initially, the body is at rest at the origin, so that means that the velocity is going to be 0 at the origin. Find the displacement at any time. So what we're going to do to start off with, we're going to start off with our function. So our function, as I said before, this time it's going to be negative f of v because the force is opposing the motion, and that's going to be equal to my mass times my acceleration. So in this case, I'm going to swap these two around so that we have 8 minus v is equal to 2 times acceleration. Alright, so let's go ahead and rearrange this now. And as we said earlier, we can replace the value for acceleration with dv dt. Now we don't want to integrate this function with respect to time because we've got velocity in our function. So we're going to rearrange this to dt dv, and this will also flip this side of our equation. So now what we can do is we can take the integral of both sides with respect to the velocity. And the last thing we need to do is to determine the constant. And it's easy enough to do that because we know that the particle is at rest at the origin. So we can substitute in those values to solve for c. Lastly, what we can do is we can factorize out the 2, and then we can use our log laws to rearrange this expression. So we're part of the way there now, but what we need to do is we need to find the displacement. So to find displacement, we're going to have to integrate velocity with respect to time, which means we're going to have to rearrange our function so that v is the subject. Alright, so now that we've got this expressed in terms of velocity, we can go ahead now and we can replace this term here with dx dt. Once we integrate that, we're going to find the displacement and we can answer our original question. Something really important to note here is that we are now integrating again with respect to t. So when we get this final function, it should already be expressed with x as our subject. Lastly, we're going to need to determine our constant at the end here. Now, if we go back to the question actually states that initially the body is at rest at the origin. So initially it is at the origin, which means that displacement at time is equal to 0 is also going to be 0. So let's substitute those values in and let's determine our value for C2. So now what we can do is we can substitute this back into our original expression and complete the question. Alrighty, there we go. So this is how we have used differential equations to find the displacement when velocity is changing. So when the force is a function of velocity and no longer a force as a function of time. So that one was a relatively simple example. Let's jump in and do a second one. Here we have a second example which is a little bit more realistic. So a car of mass 1600 kilograms is moving along a straight road at a speed of 90 kilometers per hour. So first thing I want to draw your attention to is that these units are both in kilometers per hour. When the driver, when the driver brakes, the braking force is 320 square root v cubed newtons, where v is the speed in meters per second. And that's something else that I want you to notice here is that velocity is being measured as meters per second, not kilometers per hour. After the driver applies the brakes, calculate the time taken for the speed of the car to be reduced to 57.6 kilometers per hour, and then the distance traveled in this time. So the first thing I've gone ahead and done is I've converted my units so that they are all in meters per second. So for 90 kilometers per hour, that becomes 25 meters per second. And for 57.6 kilometers per hour, that becomes 16 meters per second. So now what I can do is I can go ahead and use my function. The force as a function of velocity is going to be equal to mass times acceleration. Now what I can do is I can come in and I can replace my acceleration with the function dv dt, and then we can rearrange so that we can integrate with respect to v. Now that we have our integral, we can go ahead and substitute in the values that we know to solve for our constant. So in this case, when we have our initial time, initially they are traveling at 90 kilometers per hour, which remember is equivalent to our 25 meters per second. So in other words, when t is equal to 0, v is going to be equal to 25 meters per second. Now that we have our value for our constant, which we determined to be -2, we can go ahead and substitute in my second value for velocity now. So that's going to be in meters per second. And we can do that and determine the time that that's going to take to reach that point. So using that formula, I've determined it's going to take about 0.5 seconds when applying that braking force of 320 root v cubed. When we apply that braking force, it's only going to take about half a second to slow from 90 kilometers per hour to 57.6 kilometers per hour. So let's go ahead now and answer part B. So for part B, we're going to calculate the distance traveled in this time. I always find this really interesting, especially when they have a lot of ads on TV about how every K over is a killer. And so if you were traveling at 61 versus 65 versus 70 Ks over, what's the braking distance actually going to be? So I actually think this is going to be a really interesting one to see, because it seems like it was a very quick amount of time that it took from when you applied the brake to when you slowed down to 57.6 kilometers per hour. Let's see how long that distance actually is. So from our previous question, we already know that the acceleration is equal to -1/5 v to the power of 3/2. Some information that we can infer from our question is that when the displacement is equal to 0, the velocity is equal to 25. And I'll explain why that is. So originally, we consider this our negative time here. So our car is traveling along for however long at 90 kilometers an hour. At this point here, it starts to apply the brakes. So the displacement at this point is going to be 0. As the car continues along, it slows down. Half a second later, it reaches its velocity of 57.6 kilometers per hour. So we're trying to determine this distance here. So we're saying that that braking point is going to be a displacement when x is equal to 0. And so we know that the velocity at that point in meters per second is going to be 25. So rather than having our function expressed in terms of time then, it means that we need to express our function in terms of x and v. And we can do that using the chain rule. So here you can see we have dv dx times by dx dt is going to give me dv dt according to that chain rule. Now, as we already know, velocity is the same as saying the derivative of x over t. And so what we can do is we can replace this value with v here now. And so we're no longer dealing with that third parameter t, we're only dealing with velocity and displacement, which is what we need when we're looking at these particular values here. So let's go ahead and substitute this information into our equation now. Okay, so all I've done is I've just rearranged by dividing both sides by v. So what we can do now, we've got dv dx is equal to -1/5 v to the power of a half. And I want to integrate this with respect to v. So I'm going to flip my equation and then integrate. Let's use this information now to go ahead and solve for c. So x is equal to 0 when v is equal to 25. And then this will give us our function. Let's pop this value for our constant of C1 is equal to 50 back into this expression. And then what we can do is we can go ahead and solve for our displacement. I've completely removed time from this equation. So we know from A that our answer for that time taken was half a second. But what we do know here is that that velocity at that point is going to be 16 meters per second. So we can use the velocity now rather than the time to solve for this particular function. So you've probably seen throughout this that usually whatever value we're expressing that as a function of velocity. And that's because these forces depend on the velocity. That's the thing that's changing. So let's go ahead and substitute these values in now to determine our displacement. So final displacement that we've determined is that when our final velocity is equal to 16, the displacement is equal to 10 meters. Now this seems pretty short to me, to be honest, if we're going from 90 kilometers per hour to 57.6 kilometers per hour in half a second, and we've only traveled 10 meters. So maybe this question isn't as realistic as what we are thinking that it is. But if we go back and look at that braking force, it's probably because that initial braking force is actually quite high. Alright, so that's how we solve problems that involve using forces that depend on velocity rather than forces that depend on time. Alright guys, I'll see you in the next video.